Let's take a look at this. Oh my goodness. Now, if we wanted to do some math on this, we could calculate what the Kepler constant is for our solar system. Let's tell you what we got going on here. We've got the Kepler constant for our solar system would have the formula r cubed over period squared. That would be the orbital radius for any given planet divided by its orbital period squared. Or we can calculate it as g times the mass of the sun divided by 4 pi squared. Incidentally, if you could measure the orbital radius and the orbital period, can you guys see that kind of like how Cavendish calculated the mass of Earth? You see that we could calculate the mass of the sun here. So we can get at the mass of our sun through this process. We actually could have calculated the mass of the Earth through this process by looking at the orbital radius of the moon around the sun and the orbital period of the moon around the sun. That isn't how Cavendish got at it, but we could have gotten at it that way. Okay, so kind of neat to look at it historically that way. But we can figure out what the Kepler constant is going to be for our solar system. By the way, the mass of the sun really is going to be 1.99 times 10 to the power of 30. That really is how massive our sun is. And then if we use Kepler's third law, we can figure out how long an Earth year is if we know what the orbital radius for the Earth is. So what I've done is gone back in and said, hey, if I know Kepler's constant from part A of this question, then I can calculate how long an Earth year is based on Kepler's third law. So that's what I did. I went through and I figured out that a year is 3.1683 times 10 to the power of 7 seconds. And according to Kepler's third law, that's what it should be. So then I went back and I said, hey, there's 365.25 days in a year times 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute. And oh my gosh, that's actually not bad. That's a pretty good approximation. And people say, well, how come it only agrees to like the first 2 digits? Would you be willing to bet there was probably some rounding in my givens? That's the reason. It's because my givens were rounded off too much, not because Kepler's law is broken. But it looks like pretty close agreement. It's on the same order of magnitude. If I round off to just 2 sig figs, they're in agreement. Probably I need a little more precision in my givens. And honestly, you look at this man's lab, it's in a castle. Who's doing orbital mechanics that are still relevant today in labs that are in castles? I wish I had an office in a castle. All right. Last thing about this. This is the math, but at the bottom is the words. There are different shapes for orbits. Elliptical orbit, parabolic orbit. Now we talked about parabolic orbit. Parabolas are ones that, that's the shape of objects that crash back down to Earth again. That's not an orbit though. But if it's an orbital body that actually doesn't hit the Earth, this is a body that's going to never come back again. It's not captured. If we have 2 bodies that are similar mass that go past each other, we get a hyperbolic path. And those don't return either. I got to take the temperature of the room. Can I slide the math away? No, we still need the math. Okay, then what I'm going to do is I'm going to zoom out just a little bit. Okay, because I don't want to hurt anybody's writing. And it's nice to tie this back to geometry. Because I mentioned before that these orbital shapes are called conic sections. And literally, if you take a cone and you slice it, you can produce each of the shapes of these orbits. So we've seen these shapes in optics for focal points. We've seen it every time we look at a cone. If you slice a cone, you can get these shapes. And there's applications for orbital mechanics. It's kind of this neat thing. When you study math, and there might be like theoretical stuff in math class, you're like, oh my goodness, how could this ever be applicable? It doesn't. First of all, it doesn't have to be applicable. But it's shocking how much of it is if you go down the right rabbit holes. In terms of vocabulary, if you're somebody who does like language, when something that's at its furthest point away from the sun, that's called aphelion. or aphelion, depending on who you're talking to. When it's at its closest point to the sun, it's perihelion. The suffix helion pertains to the word to sun. When the Earth has the moon going around it, when the moon is closest to us, that's perigee. Notice peri means closest to. Perigee is when the moon is closest to the geo, the Earth. Apogee, ap must mean far from in Latin as a prefix. So apogee is when the moon is farthest from the Earth in its eccentric little orbit. There's a little bit of the Latin language there. And in your handouts, there's a little bit of a legend there for Latin word decoding. Ap is far, peri is close, G or geo is Earth, and helion relates to Helios, the sun. Okay? And to put some context on the history here, Kepler, here's his lifespan, 1571 to 1630. Some impressive figuring out happening during that time frame.